So we begin our study in derivatives here. All right, so let's quickly put some review from stuff we've been doing, you've been doing, not like us here, but stuff that you were comfortable with. Let's say you have a line, right? Any line in your graphing space right here, then a line like this got famously the equation y equals, anyone remember? What's that? Okay, mx, how's that? Okay, so mx plus b, that's the variable here. MA is fine, it's you got the name, your way to name the variables, but more traditionally we just name x, right? But anyway, so what's the m stand for? Anyone remember? Slope. Okay. So the m stands for slope. But then basically we're talking about a line, right? Even if when you take away the axes right here, then any line got sloped here, the slope is indicating where the line is pointing, right? The direction of the line. So yes, the m coefficient here is the slope. Anyone happen to remember how we calculate the slope of a tangent line? Of a line? The rise over run, right? See, there's always famously the rise, right, over run. Yep, the horizontal change right here, that's the run right here, right? And then the vertical change right here is the rise. Now, sometimes people get into a common common habit to say rise over run only, but the truth is sometimes the line may be falling down like that, right? When you're looking at the line from the left to the right, you know what I'm saying? So the point is we got to change in vertical value over the change in the horizontal value. So that's still your run right here, right? But sometimes I refer to that as fall as well. See what I'm saying? No? So in my case right here, a lot of time I precisely call it either rise or fall, right? But all of that, any of that is over run right here. See what I'm saying? No? Okay. So enough beating around with the bush right here. And then yes, your b value in this, the equation of a line. Anyone remember what that's for? The y-intercept, right? Okay, the y-intercept. The idea is, I said sometimes, like I said earlier, sometimes we may even hide away the axis, but in the end the axes are still there, right? So there's a vertical axis. So at some point on the vertical axis, your line is gonna intersect, right? That's why it's called the intercept. You know what I'm saying now? Okay, so the vertical value on your y-axis, we call it the y-intercept, but that's where the line is crossing the y-axis. Okay, fair enough. So now, that's the idea. So now just back to a line again. So I already briefly reviewed those things for you. Any line got an equation, right? Famously mx plus b, and then the m is the m coefficient is the slope indicating the rise over run, and the y-intercept is indicating if we put the axis there, right? And that's where it's intersecting with the y-axis. But now the question is, what if I want the line here? I want the line here specifically to be a tangent line. The idea now is that ever since you guys learned geometry, there's like say circle. Now forgive me that I'm not an artist, okay? But for a circle, you can always put a line that's tangent to that circle. See what I'm saying? No? Any circle, right? As long as the graph here is being in any kind of bent nature right here, then you can put a tangent line. So we already seen the idea of tangent line since the days you learned geometry back in high school, right? So you can always put a tangent line anywhere on your circle right here. What's the major characteristic of a tangent line? Anyone remember? Yeah, it touches your circle at only exactly one point, right? And so we extend that idea. So tangent to a circle, same line right here, but think about now you've been working with algebra long enough, right? Your function got graphs that bent up, bent down all over again. See what I'm saying? No? So I'm also now interested in getting the tangent line. So see this line right here, I purposely put that as one specific point like that. Now don't get me wrong, now when your curve now is no longer a circle, but it's kind of like bending up and down all crazy. It could still be intersecting the graph at some other points, right? But I'm talking about the idea is in some local area, right? In some interval that's nearby, then the graph only going through the line is only going through the graph at one point, so it's still consistent with whatever your classmate is saying, right? That the idea is we're looking for the tangent line to be the line that barely touches that curve, right? At only one point. Sounds good with that, right then? Okay. So yes, I want this line to be another tangent line. See? I want that to be tangent line. So it's only barely touching your curve, your bend function, your bend shape right here at only one point. And so now any tangent line we has equation, right? Just like that. Y equals mx plus b, just like that, right? Because yes, we call it a tangent line, but it's a line, so it has to have that equation mx plus b. But now I would like to refer a little more special over here. The slope for your tangent line is now kind of like my convention and kind of agree with many other textbooks conventions as well. That we put a little subscript t right here, right? To indicate the slope here is the slope for the, so we're talking about an equation of a line, but the line here is a line that's being the tangent. That's why the m here is an mt. To make it a little more special. See what I'm saying now? Okay. So now think about the scenarios like that. Actually, we're promoting an actual problem now that here's your function, f of x. Okay. And let's say at this point right here, x equals a. You've got a point on the graph, right? Your function is continuous whatsoever. I want to find, right? The goal here is to find the slope of the tangent line. Right? The slope of the tangent line. Then specifically here at x equals a. So a here is just some arbitrary point I put right there. It doesn't have to be a 5, doesn't have to be a 6. I'm talking about generally when we picked any arbitrary point, right? On the x-axis. At that value right there, we have a point on the graph, right? So now think about it. So we want to find the slope of the tangent line at x equals a. The idea now is that once you pick a point on that curve right here, we can place a tangent line there. See what I'm saying? Huh? Of course, my drawing is not exact, but the idea is we will be able to place a tangent line there. But in order to place a tangent line there, how big is the slope of that tangent line? You guys see what I'm saying? No? Right? That's the idea that we're getting into right there. See, so the slope of the tangent line. Just earlier I was saying I was using, so the equation has to be mtx plus b, right? Because in the end, tangent line or whatsoever line, it needs to be mx plus b, right? And I purposely use a subscript t right here to indicate that the line here is a little special. It's the slope here is the slope of the tangent line. You guys with me right there? But in the end, it's just a slope. So the problem here, the problem here we being introduced here is we need to calculate, right? Back to this problem, we need to find out what the value of the, or how we can calculate the value of the slope of the tangent line. See what I mean? All right, so let's get really closer into the situation, but I need to put that the main goal aside right here. Let me now dive further into, just think about right here in the picture, think about it, you can zoom in into a closer window right here, right? Okay, just narrow your attention to the closer window and the graph is going to probably look like this. See what I'm saying, no? Okay, the graph's going to look like that, and here's your x equals a. Okay? And again, our attempt here is to get the slope of the tangent line. I'm going to draw the tangent line here in black ink. This time here, I need a different color ink right here. So, in blue here, think about this. How do we calculate slope? You guys mentioning it to me, slope, right? The way we're doing it, rise or fall, right? Over a run. See what I'm saying, no? Okay, rise or fall. Because the graph could be rising, right? Or the graph could be falling. See what I'm saying, no? So we measure the vertical change, right? Over the run here. But then, now you think a little further from here. Is it even possible to proceed into this plan, into that work to calculate our slope of the tangent line? Can we really proceed into this way of calculating rise over run for calculating our slope of the tangent line? It's a line, got the slope just like any other slope out there, but in our case right here, can we really calculate the rise over run for our situation here? The slope of the tangent line. Okay, why not?
You need at least 2 points.
You need 2 points. Now we need to, in order to do rise over run or fall over run, right? You need 2 points because the second point is going to indicate for you how far the rise is or how far the run is, and then how far the fall is over how far the run is. But what's the problem here? So yes, we need 2 points, but what's our real problem here? Along with what you said, then we need 2 points. So what's our real problem here? The tangent.
Yeah, tangent only have 1 point, but we need 2 points.
Yeah, we need 2 points, but the tangent, that's the biggest problem is tangent only going through the graph as 1 point. See what I'm saying, no? So here's the way how we deal with that. So we need another point. So rise over run formula for now doesn't work yet. This rise over run or fall over run doesn't work yet. Doesn't work immediately yet. So mathematicians in the past come up with this plan here. So keep in mind again, our goal is to calculate the slope of the tangent line. And the biggest problem is the tangent line is only going through your graph at 1 point. Okay? That's why it's so challenging. So mathematicians come up with something like this. Right from sort of like centering right at that main point, right at that main focus point that we want a tangent line like that. They're gonna purposely shoot out another line that's going through that same point, but intersect with the graph at another point. See what I'm saying now? Okay. So now we have a line, and that's why I purposely draw the line in blue over here. This line here, can you guys obtain the slope? For that line in blue, then we can obtain the slope easily, right? Because here's how the slope goes. And then you guys are now, there's a reason why you arrive at calculus level over here, because your mind is mature enough to do these things in a more general setting right here. Now think about this other point. Of course, it's being away from that main point that we're looking at, right? So this point right here, think about when you project the x value on the x-axis right here, it's going to equal the x value of that point. It's going to be, see, some distance away from A, right? So how about generally we call that A, but plus that distance H here. You guys follow with me on that? Okay. So that means what? Guess what? That space right here is H. Right? That's why the x coordinates for this point in blue right here is called x equals A plus H. You guys agree with me on that, okay? And then again, I just need to remind you that as soon as we did that, right? Once we did that, once I put in a picture of that blue line right there, then immediately we got 2 points, right? So now label that carefully with me right here. This, well, maybe it's better that I'm doing that with red ink. So this point that we're aiming to get the tangent line at, right? This original point, this main point right here, that's x equals A. The vertical y value here is what? Y equals f of A, right? You agree? But what about this vertical height that I'm calling, that I'm putting in the dotted blue ink right here? It's happening, it's a point on the graph, right? At x equals A plus H. See what I'm saying, no? Okay. And so this vertical height right here, how do we call that? The y value here is f of A plus H, right? Agree with me on that still? Okay. So each point, so basically what I'm trying to explain now is that point, at that point right here, we're talking about the coordinates A, comma, f of A, right? That's one complete point. The other point here in blue is sitting at coordinates on the graph, is sitting at coordinates A plus H for the x at value right there, comma, f of A plus H. Are we good with that? Okay. And so now after so much explanation now, I need you guys to pay a little closer attention here. Now with the blue line, are you able to obtain the slope for the blue line? Because now we got whoever that said earlier, we needed 2 points, right? So now this blue line right here does go through the graph at 2 points. So how do we calculate the slope of that blue line? That's why I'm writing that in red, in blue ink right here. The slope of the blue line, you've been saying it, right? Yeah. Rise or fall or run, right? But then now, so that's just the more general way of saying it. Now precisely into the problem here, how do we do it? Go ahead and complete your work.
Changing y minus changing
x. Changing y minus changing x. I'm still not
changing y over changing x.
Good. Sorry. But specifically now I already tear it down to this. How do we express that?
F of A plus H.
F of A plus H right here, right? Go ahead.
Minus F.
Minus f of a. Yes, it's a change in y right here, but now specifically we're talking about in this specific situation now, we got f of a plus h, right? Minus f of a. You guys see what I'm saying now? And over the run, so who can complete the run for me? The run is just h. You know what I'm saying? Now that's just your familiar rise, overrun, or fall overrun, whatever, right? But now into this interpretation right here, we derive that formula that says f of a plus h minus f of a over h. See what I'm saying? Okay, so from your pre-calculus days, your instructor should have mentioned, at least you have seen this setup before, right? Do you remember what it's called? Yes.
The difference quotient.
It's the difference quotient. This thing from your pre-calculus 1 day, referred to as the difference, right? Quotient. I don't blame you with that. Faded away, but here it comes back, right? It's called the difference quotient. But more precisely, the difference quotient at x equals a. You know what I'm saying? No? It has a specific meaning for that setup right there. So it's still, right? You all gave me the correct input right there, but I just really want to tear it down to this precise level. See what I'm saying? So it was the rise over run, right? And then or the changing y value over the changing x. And now precisely to this problem, the changing y is indicated, is calculated as f of a minus a plus h minus f of a. Divide the difference by h, the changing x. Sounds good? Okay. But so, here's the problem. We got the rise over run or the fall over run, the changing y over changing x thing, but, and I wrote it in blue for a reason right here. Did we get to our goal, getting the slope of the tangent line? We didn't, right? Because this line in blue right here, indeed, I wonder if you guys also recall a term. The tangent line, according to what you told me, right, according to what we've been knowing, is only going through the graph at 1 point, and that's why it's dangerous right here. But this line in blue is going through the graph at 2 points. 2 points. Do you recall what that kind of line is called? Anytime that your line is crossing the graph, so what, at 2 points. Or crossing a curve at 2 points, do you remember how it's called? I don't blame you if you don't remember, but share with me what you got. Hold back your memory. So we got tangent versus some, anyone remember? So curve is bad, right? Going through only 1 point, that's tangent. But the curve is like that, going through 2 points. Okay, I just replied. Secant. Okay, the secant is, you know, the opposite from the tangent line. The secant is going through the graph at 2 points. See what I'm saying? No? So the blue version, the difference quotient that we fire up right here, the difference quotient formula we fire up right here, is only serving the purpose of calculating the slope of that secant line right here. It's not yet the tangent line, and you guys have already realized it, right? So here's what people do. So it's still going to be the blue version right here. I'm not happy with the slope of this blue line. See what I'm saying now? So the idea allowed me to do another blue version, okay? Another blue version. And then the picture is going to get a little busy. So how about, I want to erase this, just that part, okay? I'm going to create a different blue version. How about, I'm going to put a blue line kind of still going through that point, but crossing right here on the graph. See what I'm saying now? Still going through that point where we aim to put the tangent line at, right? But it's crossing at another point. How about here? It's still a secant line, isn't it? Right? In the way how I put the picture, it's still a secant line, right? Still a secant. The way how I get the x value there, the way how I get the x value here is still, you can generally call that x equals a plus h. See what I'm saying now? But what just happened to the h? Well, it's still the h doing the difference here, right? And calculating the slope is still f of a plus h, right? Minus f of a right here. Minus f of a. So f of a plus h minus f of a over the run h. But what just happened in the picture here? Yeah, the slope of the secant line got closer to that destination, right? But what I want you to see a little further is that the idea is from the two blue versions, the earlier blue version that I made, right? We got a bigger h. You guys see what I'm doing now? And then with this new blue version, I made h smaller, right? And that's how consequently you start noticing that the slope of the blue line right here is still a secant line, but it's getting closer to the slope of the tangent line. You guys following what I'm explaining with that? And so if I'm not happy with that, I can go even closer. I can go with something, right? I can come up with something like this. So still, another blue line right here. And my picture now is going to get extremely busy. I'm going to draw with my best. Another blue line right here. See that now? That third blue line right here, it's still a secant. Right? It's intersecting with the graph at 2 points. It has an x value on the x-axis here, namely called x equals a plus h again. But once again, what keeps happening to h here? H keep getting smaller and smaller. See what I'm saying? No? And then as we get an h smaller and smaller like that, then yes, I agree with what you're observing right here. As we keep getting h smaller, sort of like the secant line rotates, right, to get close to the actual slope of that black line being the tangent line. You guys follow with me on that? So now, just simply the difference quotient, right? Just simply the difference quotient is not enough, right? It will permanently stays at the slope of the tangent, slope of the secant line. But now, what the extra step we're doing here? The extra step we're doing here for the actual so it has been this is slope of the secant line right here. But now the extra step we're adding on top, we're letting h going smaller, right? Is that concept so familiar? We're taking the limit as h goes to 0 here. You know what I'm saying? No? Okay, so the major difference between the slope of the tangent line and the slope of the secant line is the slope of the secant line just stay fixed with that. But slope of the tangent line, after setting up the difference quotient, right, we have to let h get close to 0 as a limit problem. That's why any calculus course like that, right, start out with learning about limits, because you need to be fluent with that concept before we move on. Okay? But so now this famous formula now will serve that purpose, getting you calculating that slope of the tangent line. You guys see how things being derived like that? Okay. All right, and you can see really, I introduced a title about discussion here is we're talking about derivatives, but I didn't tell you anything about derivative yet. By far, we're only looking at the slope of the tangent line, right? And we focus all of our attention into getting the slope of the tangent line. So along that way, let's do one example. Example 1 right here. So how about you're given the function here is to be f of x equals x squared. So before I complete my example, the instruction right here, you guys familiar with the graph of the graph of the x squared function? What does it look like? Yes, yes. So everybody knows it, right? It's this thing right here. So keep that picture in mind. So you're given that f of x being the x squared function. So let's just simply, I'm asking, find the slope, right, of the tangent line. To f of x given. And let's call it part A right here. X equals 1. So same example, I'm intending to get you guys another try right here. All right, so let me bring up a quick picture over here so that you can understand what's going on first. All right. Here's our blind graphing space, right? So just as you have agreed, so now let me pop out the graph right here. The graph for your x squared function is like that, just like how everybody has agreed earlier, right? So there's your graph right here. So I'm talking about at x equals 1. So right here, when x equals 1, we're going to have a point right there. Am I correct? Okay. So now let me put that point in. Right? That point is at the A 1 F 1. That's the way how we conventionally put in the point, right? The x is the given value right there, and then the y value is the function output. So we got the point right there. See, 1, 1. So when x equals 1 at that point on the graph, here's how I'm showing the tangent line is going to look like this, and allow me to hide the equation of the tangent line. But see, we should be able to come up with the equation completely later on. But the idea now is that if we put, right, if we would put a tangent line there right through that point 1, 1, or right through that point on the graph, right? Then how big is the slope of that tangent line? See what I'm saying now? That's the idea, right? That's the plan for our work there. All right. And so what we've had earlier was simply just a graphical interpretation of that, a demonstration that was done graphically. But really to calculate that, right? Because remember, in order to find the complete equation of tangent line, see? The truth behind the scene that how you saw it on the screen is that I had to know the equation in order to put that line precisely there. And so without knowing the line, I mean the equation of the line, there's no way to put that line there. That's why we need to go, instead we calculate the slope, right? So famously, according to what we've learned earlier, the slope of the tangent line, right, at this given value right here, the way how I'm doing it, first we're going to produce a difference quotient. The difference quotient says f of a plus h, right? But what's a in our case? Now a is 1. You guys following? Right, so now I'm producing f of 1 plus h to be precise, right? And I should have highlighted that in red ink. Right? F of 1 plus h. That's our center point, the point where we want the tangent line. We're subtracting, right? F of 1. You guys agree on that right there? And we divide by h. So this is the difference quotient, that famous difference quotient. But sadly, this is only giving me some slope of a secant line, right? So to really get precisely into that slope of the tangent line, we have to do the limit problem by setting up that limit as h goes to 0. Okay? All right, so now once we've had, so I gotta say, this is the very fundamental setup in here. Anytime that you're calculating the slope of the tangent line, sadly, we gotta set up this difference quotient first with the limits problem as a limit problem, right? The difference quotient as a limits problem. And so now with that instruction, right, the next step is gonna become what our function is x squared function, right? It has that graph that you already agreed earlier. But now with the 1 plus h expression from your pre-calculus, you learn that substituting it in, you can go 1 plus h all squared, right? That's how we're substituting in that expression right there. Minus 1 all squared. See, this is precisely f of 1 plus h here. And this is f of 1. We're taking that difference and divide by h. And then again, we're just now working with the algebra, so I haven't done any limits. And the problem needs to be a limit problem, so I'm leaving that limit operation hanging in there. So this next step right here is also quite vital because that's how we transform from that starting formula in general, right, into the actual, we're incorporating the formula here into our actual function here. See what I'm saying now? And that's how I arrive at that particular formula. But now when it comes to this time, with this point right here, then you guys, on Scratchboard, you guys have a lot of different ways of how to tackle it now, but you need to, in the end, the 1 plus h all squared in order to move on, right? The 1 plus h, because clearly, as a limit problem, we cannot just simply apply the basic limit laws here, right? You see the denominator goes immediately to a 0 limit right there. That's why the algebra techniques we've learned back in the days, right, is going to kick in and be useful for us here. So guess what? You guys still remember how to FOIL this up? Yeah? Okay. Take your time, how about half a minute, FOIL that out for me. Yes, please.
H squared plus 2h plus 1.
H squared plus 2h
Plus 1 squared.
plus 1 squared, which is just 1, right? Do you all agree? Okay, thank you. Yes, that's how we FOIL that up. And so now the 1 plus h all squared is FOILed into h squared plus 2h plus 1, right? And then we're subtracting. You guys agree? The other one for here is simply a 1 needless to say, right? Divide by h still, right? H going to 0. So really all of a sudden I have driven your attention into just simply doing a limit problem right there. Sounds good? But that's where limits need to be fluent here in order to move on. And so now what else can we do? Still, we're not in a safe zone yet, right? For taking this limit right here, because that denominator is still going to 0. But then at least I can cancel the 1 away, right? And so now that becomes h times h plus 2 right there. Now I kind of skipped step a little bit, but I canceled away, and then of course we're going to have 2 terms remain, right? And those are all having a common factor of h right here. You guys following? And that's the reason why I kind of combine 2 steps into 1 right there. I cancel that, and then I factor out the h right there. So I'm leaving behind h, and in parentheses h plus 2. Are we good with that there? Okay. And then I'm dividing by h. And this is where we start seeing how we can cancel the expression and make things land into a safe zone right here. All right, so I think I have enough space for the next step right here. So now, yes, the h here will cancel. In the next step, we're looking at just h plus 2, right? And this remains limit prop right there. But now we're at the safe zone right there, right? We have landed into the safe zone in terms of taking the limits prop right here. So now, with the basic limit laws, what should this give me? You just go now, and I can get, well, when limits now become just a small part of a bigger, much bigger work right here, then we can start going loose a little bit with the steps. I'm not going to be too bothered with how you write your steps here. See what I'm saying? No? So, it's simply just going to go like 0, right? Plus 2 right here. Sounds good? And see, combining with what you have learned previously about continuity and all of that, you have landed the point out, I call it safe zone, because now this final simplified version right here is a safely continuous function with that, where you can work it like you're substituting the limit value in. Am I making sense? So now your final limit is 2. The final limit is a 2, right? But remember, the reason why we led ourselves into a limit problem, the whole reason we arrived at the limit problem simply because we wanted the slope of the tangent line, right? And so we went through all of that math right here, and we come up with the 2 right here. So the 2 at this point for ourselves is not only a limit problem, but the 2 here is the slope of the tangent line of yours right here equals 2. So you found an answer. You guys following me on that? Okay, so I still have that picture right here on my computer screen right there. Let's have a look at that. And that's the reason why I'm leaving the grids on right here for my graph. But you can see that that's from there that blue point is, right? So with that blue point right there being at 1, 1 right here, this line in green, we didn't know the complete equation yet, right? But at least I call it it's a tangent line, the graph of the tangent line. So does that seem to have a slope 2 riser? It's a positive slope, right? By the way, you guys calculated that, and that final limit turned into a positive value, right? And we said it's a slope. So the slope has a lot of meaning with that. When it's positive, it means the line goes rising from the left to the right? So does it look like 2 spaces up right there? Over 1 space over? So without knowing the exact equation of the line, we're already convinced that the slope for this tangent line at x equals 1 here, right, is 2. Sounds good with that, like that? Okay, so you guys think that we can start speeding up the process a little bit for the next problem? Right, so now to continue with the example, that's called a part B. So that's all that we want. The main instruction is we want the slope of the tangent line, right? But here we're gonna really want to have a good taste at various different points. How about at x equals -1? You guys with me there? Okay. So we switch to a different point on the x-axis. So think about it. If we're working as a robot right here, then here's how it goes. We just go straight into the formula, right? We want the tangent line being placed at x equals -1 on that same graph. So here as a formula, slope of the tangent line, right? We need to fire up that difference quotient, but this time I'm changing to, see, a plus h, right? But a is -1. You guys with me there? Right? -1 plus h. Just write it down in that exact form how the formula looks. F of a plus h, right? Minus f of a. And so a in our case here is -1. So I'm subtracting f of -1, right? That's divided by h. We're taking the limits as h goes to 0. Okay? And so now when we're applying that into our specific function, for example 1 here, then it means the slope of the tangent line will be calculated as a limit problem where h goes to 0. But now f of -1 plus h gives me -1 plus h all squared, right? Minus, or take away -1 all squared. See, you see how I use parentheses very carefully right here? I highly recommend you guys do the same. Like that. Right? Use parentheses as anytime you do any sort of substitution. And then we divide by 8. Right? So now we have an actual limit problem here with the proper variables and all that. I want you guys, and again, you can notice that it's completely dangerous here because we cannot apply direct limit laws, right? So we have to find a way to simplify it down like that. So why don't you guys take your time foiling out this -1 plus h all squared? Okay, please.
H squared minus 2h plus 1.
Okay. H squared minus 2h plus 1, right? I agree. And we're subtracting 1, right? Thank you. put over h, that h, limit as h goes to 0 again. All right? Now I can put this away. So once again, the algorithm is going to come in, cancel the 1 away, right? And then allow me to combine multiple steps in one right here. So I'm going to factor out that h as well along the way, right? So in my next step, I'm looking at the limit problem. We've got h factored out, we've got x, I mean h minus 2, right? Over h. And this is the limit problem as h goes to 0. Yeah. Okay? So of course, needless to say, we cancel the h's away, right? And that runs into h minus 2. We take the limit as h goes to 0. Sounds good? So now, that is clearly a continuous function, right? So we can easily calculate that limit by substituting values in. Okay, so it's 0 minus 2, which is -2. Sounds good to me on that, okay? Okay? So once again, we've done the limits work again. We come up with the final limit, but what does that mean? It means that our slope now is -2 and x equals -1. You guys see the impact right there? I mean, keep opening the screen right there. It's going to take time for me to wait for that screen to roll up and down. But earlier, in part A of the example, think about it. The reason I put these problems in one example is that simply because here's the graph for your f of x equals x squared, right? When x equals 1 about here, see, we got it. If we would shoot out a tangent line, right, it looks like right about a positive slope. When we're looking at that line from the left to the right, right? And now in part B, we no longer stay at x equals 1 on the graph. We change to x equals -1. The idea is, see, on the graph, you can change to different points on the graph, right? So now changing to x equals -1 on the graph. Okay, once we successfully found the line here, the tangent line is going to have for sure a slope -2, which agrees with us. You guys following what I'm trying to explain right there? All right. That's our result. Yeah. So now we have a formal definition. The derivative of f of x at x equals a. At a given point, the derivative, so that's the new term here also I'm introducing, right? We've been looking at tangent lines and slope of tangent line and all that, but then all of a sudden I'm introducing the derivative. So the derivative of a function of that given function at some given point over here, and then the derivative has this symbol. So the function is f of x, right? But here at a, so I'm going to substitute a to the function, but then it's being the derivative. I use this symbol, the first symbol I introduced for you guys, f prime again. Right, so f prime of a, it's called the derivative of the function. So the derivative of the function is given by f of a plus h minus f of a divided by h, and take the limit as h goes to 0. Okay. That's the way how we calculate the derivative of a function at a given point. Okay. And so, also, I give a new definition. So this is how we define what the derivative of a function is at that specific point given. So do we notice anything connecting with what we've been doing? The derivative of the function at that given point is nothing but just what exactly the slope of the tangent line at that point of there. So now instead of calling that with a lengthy name, slope of the tangent line at x equals a, slope of the tangent line at x equals a, right? We call that for short the derivative, right, of the tangent line. I mean the derivative of the function at a. So as a remark here, something to keep in mind. The derivative at a, right, is the slope of the tangent line. Slope of the tangent line to the function f of x at x equals a. That's the exact same word, or even for short, f prime of a equals mt here at x equals a. Okay. That's something to know. It's not just some loose term. It's precisely the same like that. That's what I'm talking about. Now we're gonna look at example 2. So example 1 was entirely about we got a function given, right? And we find in the derivative. I mean, we find the slope of the tangent line at this point and at that other point, and more precisely, I call it. We find the derivative, right? So now let's look at example 2 over here. I'm going to start out with, and let's use the same familiar function. F of x equals x squared. Start out with that function again. So now we want to find the equation. So no longer the slope, no longer only the slope. Find the equation of the tangent line. To f of x. Okay. Part A over here at x equals 1. So we've had this picture from the earlier lecture when we were looking at example 1. So here's our famous x squared function, right? You guys all with me on that trick there? And then when x equals 1, see, so I assign that value right here. So at that specific x value equals 1 like that. So of course we have a point, that point right there, that popped out, right? And that's going to be our tangent point. So formally speaking, we call that point right there 1, 1, the tangent point, because right there I want a tangent. So see, right now machine knows how to put the tangent line there, right? That line in black color right there is being our tangent lines. So we want to come up precisely what equation that is. That's the whole purpose of this problem right there. And so being a line that we always famously be the mx plus b. So what is the complete mx plus b? See what I'm saying now? The complete mx plus b that generate our line right here. So that when we put it on the graph, right? When we put that through this tangent point, it's going to be completely tangential, right? To that to the curve right there. And that's the whole goal of this problem. Right? So that's the idea for our problem. You see, what we're looking for, what we asked for is the equation for tangent line. Okay? So yes, the starting goal, I mean the main goal we're looking for, right? Y equals mtx, right? Plus b like that. Any line has that famous equation y equals mx plus b, but I'm talking about here being the tangent, right? The line we're about to find right here. The line we're about to complete the equation here. The equation right here is a tangent line to that function. That's why I put that little special slope right here. I call it mt. Sounds good right there? Okay, and so now the reason I stay with the same function because I don't want to take too much time of yours here so to restart the calculation. But so the first stage, sort of like it set a routine for us. The first thing is to figure out how big the slope is for any line, right? We got to figure out how big the slope is. And so now we can just make a quick note right here that we recall from the example 1 right here, right? And that was example 1a, that's what I'm saying now. And the slope of the tangent line is famously known as the derivative, right, of the function at 1. See, the value is a x equals 1, right? So at 1 right here, the slope of the tangent line is the derivative at 1 of the function at 1. And so, like I said, from example 1a, we already calculated and finished all the way through, even though it was supposedly the whole lengthy limit process, right? That comes out to 2, isn't it? So your first step right here, identifying or calculating the slope of the tangent line, we already got that down, right? It's 2. We good with that still? And so now, but after the first step right here, example 1, we stopped right there once we found the slope, but now the slope is only part of a bigger problem like that, so we have to advance on, right? So now, I put on the picture earlier that you guys have seen it. So there's your graph right there, right? And there's a tangent point, see, and the line is going through right there, see what I mean? Okay, so the picture already showed the tangent point, but let's calculate that precisely. Let's get into a good routine of calculating it precisely. We know for sure that the tangent point is at x equals 1. You guys following? Okay. But then the other value is supposedly the function value at 1 right there. So now tangent point, I call that t points. Right? So t points for tangent point. You're gonna substitute x equals 1, right? So x equals 1, but y equals f of 1. So you substituted the value, the given value for x, right, into the beginning function right there, not the derivative. So we're looking at y equals 1 square right there, which is also 1. So the tangent point now is completed, 1 comma 1. So that point here is 1 comma 1. So you know that single point where your line is going through, right? And so as this problem right here, I'm introducing not only the problem, but it's also introducing the basic steps of how to get the problem done. So the first step, we need to obtain the slope. Okay? And then the next step right here, we need to identify the tangent point right here. And the way for doing that is substituting the given x value, right, into our original function, and we get the tangent point. And so now here's the third step right here. Now we are about to complete the equation. Now completing the equation, we have 2 different routes here. So allow me to show you guys the most common route right there, and then I can also mention spare some time mention the other routes. You see your line here, the idea is when x equals 1 and y equals 1, with your line, at this point, your line is y equals 2x plus with some unknown y-intercept, right? Because once you have found the slope from the earlier steps, then your line will be a little more completed, right? It's got now the slope, so it will become y equals 2x plus some b. But now, this line is meant to go through, it's supposed to go through that tangent point at 1 comma 1, right? 1 for x and 1 for y. And so now I'm going to substitute that pair of x and y, right, into the equation here, x for x, y for y. Okay. And so substituting that equation, that point, right, into the equation, I'm looking at 1 equals 2 times 1, right, plus b. Are we good with that? Okay. And so now from there we can solve for b easily. The y-intercepts here, right? Now going to come out as b equals 1 minus 2, right, which is a negative 1 right there. Okay, so we substituted that tangent point. That's why tangent point got to be found before we attempt make our last attempt finding the complete equation right there. So sort of like big step number 3 is here, like completing the equation. So now the final equation, right? The final equation here is going to be y equals 2x, right, minus 1. That's the complete equation of tangent line. Okay. Sounds good. I want to mention for something else. Now let me hide that thing behind the screen again. We need to just stay on this board here. See, so I'm still talking about step 3, where we identify the equation of tangent line. Alternatively, we have a different route to get there. You guys remember the point slope form of your equation? Right? Let's say your line equation goes through one point. Say we call that point x0, y0. That's the coordinates of that specific point, right? And then one thing about your line here already has a known slope right here. Has a known slope m right here, right? Then the point slope equation goes like this: y minus y0 equals m times x minus x0. Okay, that's called the point slope equation. See what I'm saying there? Okay, so how is this useful in our work? So I'm talking about, this is step 3 right here. Earlier you already saw the answer to the solution, but now I just want to give a different alternative. So it all depends on your accountability. So the tangent line that we found with slope 2, right? And it's supposedly going through 1 comma 1. And then the slope for your tangent line here is m equals 2. You guys follow it? Right, for your specific tangent line. So you can just throw that immediately into the point slope. Y minus 1, y minus y value equals 2 times x minus 1 again. Right? Point slope equation. And then from that point slope equation right there, you're going to make your way, right? Minus 1 here, but I'm going to distribute that 2 for each term right here. Right? Looking at 2x minus 2. You guys read that? Right? And then I'm adding that 1 to the other side. That we lead that to y equals, right, 2x minus 1 again. What I'm saying, I'm talking about, yes, we prefer the final equation to be in y-intercept form, but then we can go through the point slope form right there to derive our equation. So it's a slightly different route right there, right, to arrive at your final equation. You guys follow my argument again? So now let's bring it on screen right here. So now with your tangent, see, this is the reason why I have that line here, simply because I made decimals to do that, but there has to be some equation, and I didn't show the equation yet. So now let me purposely hide that line away, right? The equation we found, let's see if the equation we found truly is the tangent line that goes through this point here. So what we found is y, right, equals 2x minus 1. The line in blue that's just now popped out right there. You guys see that there? Okay, so now once we found that, the equation goes right through that tangent point, and yes, it does appear to be completely tangential to that curve right there, right? At that specific point, y, 1 comma 1 right there. See what I mean? Okay, let me move the mouse cursor away a little bit so that it won't interfere with these point right there. Yep, so now it shows clearly, and then there's your point. Right, there's your point right here. Right, or I can even zoom it in a little bit, right? No matter how far it zooms, it's still gonna just go tangential with that point right there. Right? And so that's how we're done with that kind of problem. So now let's try again. Okay, so how about, I'm gonna call it part B, but it's a completely brand new problem. Still on the same function right here. Let's find the equation or the tangent line, right? That's tangent to the function at x equals 2. So, for this problem right here, once again, what we need to complete this equation y equals mx plus b, right? And the slope here is a special slope, it's the slope of the tangent line, so it's just a good habit to put a capital T subscript, capital T into your equation right there. You want y equals mx plus b. We need to figure out what m is and what b is. See what I'm saying now? And that's where, so now first step right here, we need to figure out the slope first. Anytime you're coming up with an equation or tangent line, I mean of any line like that, right? It's not only tangent line. Tangent line is the concept for calculus, but coming up with equation of a line like that, right? You should have learned that way back in your algebra days again. So now the slope here is the first thing to find, but now to obtain that slope, that is the derivative of the function, right? At 2. You guys following? That is the derivative of the function at 2. That's the starting point. But then we haven't had any work done previously on this, right? Specifically for this function, we haven't calculated the derivative of the function at 2. So now we're going to have to start the problem from scratch. See what I'm saying? So the setting up point for that is, once again, you see our A value is 2, right? So we go f of 2 plus h, right? Minus f of 2. We good with that there? Okay? Divide by h, that difference quotient right there. We produce a different quotient, and then we take the limit as h goes to 0. So this problem right here really put us into that practical situation that we have to start everything from scratch. Yeah. And so now in the next step, it becomes, yes, it's a limit problem for 2 plus h, all squared minus 2 all squared. Right? We take the difference, divide by h, right there, we're letting h go to 0. So now that further means that's a limit problem right there still, right? This 2 plus h all squared can be FOILed out into 4 plus 4h plus h squared. And then we're subtracting 4 away after that, squaring that 2, right? And then over h. Would you guys like some time to verify how I FOIL that 2 plus h all squared again, or you guys feel comfortable with that? So now after we FOIL, we arrive at that. So in the next step right here, still, it's a limit problem, right? H go to the limit. The limit of h go to 0. Now I have the opposite terms here got cancelled, right? So I'm combining steps a little bit. After cancelling out these two remaining terms, right, has a common factor. You guys all seen that? Okay, so I can factor out EH, right? And we go 4 plus h, and then divide by h. Right? So that means now I can cancel the h common factor from both numerator and denominator, and that gives me limit as h goes to 0. Of 4 plus h, and this is where we can safely find the limits, right, without worrying about having a 0 limit in the denominator, or we can work just like we're substituting it in. And so now the final answer comes out being 4 for this limit. Okay, the answer to that limit problem is a 4. But what does that mean? That means the slope of our tangent line, right, for our tangent line that we're looking for to complete the equation here has slope 4. It's a pretty high rising line again. Sounds good? And so after the slope, sort of like stage 1, now we're going to look for the tangent point, right? So tangent point right here, we got at x equals 2, given in the problem, right? The y value will come out by simply substituting x equals 2 given into the original function, f of x, right? Not the f prime. So I go y equals f of 2, which is 2 all squared, which is 4. Now you got a tangent point at 2, 4. That's our tangent point then. right? So in this case right here, the last step here is to complete the equation. So our equation by far, right? Supposedly y equals mtx plus b, but now mt is found to be 4. So the tangent line. So now it's going to be a 4x plus b, right? So by far the equation has gone to that far right there. And so now keep in mind this equation will go, this line will go through that point of 2, 4, right? And that's why I'm going to substitute 2, 4 into the equation. So x for x, y for y, so I'm looking at 4 equals 4 times 2 plus b. Right? And so I went with my own approach I'm more comfortable with, but I pointed out the other option right there. So if you're more comfortable with the other way, you go with that, right? With the point slope equation. And so here, that's going to give me b equals -4. You guys all agree? Right? After subtracting it out right here, so your final complete equation of tangent line, y equals, right? 4x minus 4. Okay. So that's a lot faster, right? So this problem right here, we have to, invent everything from scratch, right? So the slope is always the first thing, and that's where the derivative comes in. So for the rest of the quarter, keep my words with you. For the rest of the quarter, we will keep learning about derivatives, more derivatives for the rest of the quarter, but there will be always quite a few occasions where I keep hitting you back with the find the equation of a tangent line. Because the tangent line is so important as a problem. That's the original motivation for a mathematician in the past to come up with the idea of derivatives. Okay? So anytime that you run into a tangent line problem, find the equation of tangent line, that's your standard step. First, you get the slope, and that slope is done by getting the derivative. Okay? And then after that, we get the tangent point, and after that, we complete the equation by substituting the tangent point in there. Okay? All right. So now the tangent line problem. Let's put a pause on the tangent line. Let's move on to a different kind of problem. It's still all about derivatives. Now it's all about getting you guys comfortable with different kinds of ways to get derivatives done here. So how about example 3 here? Okay. So how about we're given another function, x cubed minus 2x. Okay. So with that function given, let's find f prime of a at a is 1. Great. So we are instructed to find, what is this called again? Yes, it's f prime of a, right? Or another way of saying that, it's the derivative. So f prime of a is the name of the symbol right there, right? But it's really, that's called the derivative, right, of the function at a. So get comfortable with that. Right? So now, to find an f prime of a right here, or the derivative of the function at a. And so the idea is that here we have, in part a, we have a specific a given being at 1. So I'm talking about, let's find the derivative of the function at 1, right? You guys would know that, right? So according to the definition we've learned, it never hurts to keep repeating the formula. We need f of what? 1 plus h, right? Minus f of 1. You guys see the repetitive work that we keep doing with that difference quotient right there? We divided that by h. We take the limits as h goes to 0. So I always have to start out with that famous formula with our designated given a value, right? Substituted it. And now from that point, we have a further instruction. The function now is x cubed minus 2x, right? We're going to substitute that in here. So my entire intention for this is to get you guys comfortable with doing the same difference quotient here on larger function, more complicated function, that's all. So we're looking at here 1 plus h all cubed minus 2 times 1 plus h. Do you agree with the way how I substituted 1 plus h for my function here? Okay. But then don't forget, so that's only f of 1 plus h, right? We need to subtract. And now we're looking at 1 cubed minus 2 times 1. I substituted 1 into my function as well. So this is f of 1 plus h minus f of 1, right? That difference there I'm going to divide by h. We go limit as h go to 0. Why don't you guys take about half a minute? Your algebra should be strong enough for you guys to be able to think of the 1 plus h cubed right here as 1 plus h times 1 plus h times another 1 plus h. Why don't you guys take half a minute, FOIL that out for me, FOIL that out. Right. Yeah? What do you have?
I got h cubed plus
Okay.
3h squared plus 3h plus 1.
I agree. So that takes care of the foiling on that cube right there, right? So simply take your time multiplying out, multiplying out, multiplying out. I agree with your friend's result right there. And then with that, I'm going to subtract. Now the 2 multiply with each term, the minus 2 multiply with each term there, right? Giving me minus 2h. And then now these are just one constant value, right? 1 minus 2 right there. So it's, and then with the minus, so 1 minus 2 is a negative 1, and with the not minus, so now it's a plus 1. You guys are all good with me on that? Right. And then we put all of that over h, and the problem remains as a limits problem right here. All right. So now lots of cancellation will happen so far. The 1 plus with the 1 cancel with the 2 right here, right? These are canceled, right? We got some like terms here to combine. See what I'm saying? No? So I'm looking at limits, h goes to 0, right? H in the denominator here, combining these like terms we're looking at. Well, the first term is h cubed, still there, 3h squared, but plus h right here. And then I realize there's a common factor h throughout 3 terms here in the numerator, right? I'm going to factor it out. The limit operation remains the same, right? I haven't done any limits work yet. I'm just beating around the bush with the algebra. We're factoring out h. I got h squared plus 3h, right? Plus 1. And then you're putting that over h. Now we can cancel the h away and letting ourselves into a safe zone where you can calculate limits as a substituting values in, right? So limits go to 0, right? H squared plus 3h plus 1. Right? So now the limit work is just one small part of a bigger problem. So I'm not going to be too bothered about how you find that limits. It's going to come. It should come out being just what 1, right? See 0 all squared plus 3 times 0 plus 1. All right. So now what is the meaning of this? This is our f prime of this is f prime of 1 here. We found it. Well, x equals -2. The exact same instruction like that. We want to find f prime, the derivative of the function at x equals 2. Meaning what we're looking for here is f prime right, at -2. Okay, so that. Okay. So again, the starting point. See, this is we're asking for the derivative, right? The derivative of the function at -2 here. So the way we're finding that, f of -2 plus h, right? Minus f of -2. Dividing that difference by h. We take the limit as h goes to 0. So into the quotient right here, that means what we're looking at is the limit problem. H goes to 0. Now I'm looking at our function here is the x cubed minus 2x, right? So now x cubed is going to be minus 2h, minus 2 plus h, all cubed, minus 2 times minus 2 plus h. This is f of minus 2 plus h. You guys with me on that? And then I'm going to need to subtract, right? And then f of minus 2 all cubed, minus 2 times minus 2. Right? Divided by h. Different quotient, right? Yes, once again, take your time foiling out the minus 2 plus h for me. This minus 2 plus h all cubed. Think of that as, or you can also think of that as an h minus 2, because minus 2 plus h is the same as h minus 2, right? So think of that as h minus 2 times h minus 2 times h minus 2. Take about another half minute to get that foiled out for me.
We have h cubed minus 6h squared plus 12h minus 8.
I agree. Right. So now with that, I'm going to subtract. Right. So again, the minus 2 here gets distributed with the 2 terms here. So we're looking at plus 4, right? Minus 2h. You guys following? And then here, that's minus 8, right? Plus with the 4 again, making it the minus 4. So it's plus 4 here. Minus 8, right? positive 4, making it a negative 4, and subtracting a negative 4, making it a plus 4. And then we divide that difference by h. That is a limits problem as h goes to 0. So lots of cancellation can happen over here. Just can't make the h look any better. Okay, so these opposite terms, right, cancel. And 4 plus 4, opposite with minus 8, right? The like terms here, right, will combine, making it a plus 10h. So in my next step, right here, yes, I'm looking at h cubed minus 6h squared plus 10h all over 8 here. The limit as h goes to 0. So now I can easily factor out the h, right? So factor out the h, we got h squared minus 6h plus 10. Dividing that by h here. 0. So in the next step, limits, right? H goes to 0. So h squared minus 6h plus 10. It was all due to that. We cancel the h's here. And so now the answer comes out quite simple, right? As h goes to 0, that terms go to 0, that terms go to 0. The last one here goes to 10, right? So your final derivative value is 10. So what I'm saying out loud now is that f prime for this function, right? For the function we defined on the other board, the f prime of minus 2 comes out being positive 10. You guys good? It also means the slope of the tangent line, but here I just want to focus on getting you guys comfortable with playing with the algebra to get your limit problem done like that, right? As a derivative problem, simply as a derivative problem. But so by far, anytime it comes to calculating the derivatives or the slope of the tangent line at a given point, go through that limit definition is the only way, right? We're going through that limit setup for that. That's why famously you will hear, and later on when I start posting the assignment, you will see, find your derivative using the limit definition, find a derivative using the limit definition. That's the limit definition I'm talking about. Okay? Right? You're setting up that starting limits right here, right? And then we start working it down to your way of reducing the algebra and all that. Sounds good? Right. Let's look at another tangent line problem right here. Let's call it example 4. We got x to the 4th minus 4 x cubed. And so we want to find the equation of the tangent line. At x equals 1. All right. So we are doing another tangent line problem, right? So the way how we work, just so like that problem in example 2 that I brought up earlier, right? There are 3 major steps. First, you got to identify the slope, right? The next thing, get the tangent point, and the last thing is you substitute that tangent point into your equation to complete your equation of tangent line. So just like that, ultimately the goal here is y equals mtx plus b. We need to complete that equation. We need to find out what the slope is, then to find out the y-intercept value is, right, to complete the equation. So that's why, so now as a starting point, the slope here is calculated as the derivative of the function, right? But then this time at where? At x equals 1, right? So mt equals f prime at 1. But then f prime at 1, right, the derivative of this function or of any function, and the value is calculated as a limits problem on that the difference quotient. So here f of 1 plus h minus f of 1, right, and we're dividing that by h. Right? So the slope of the tangent line as a as a good highlight is calculated as a derivative, but then the derivative is calculated as the limits problem of a difference quotient. And so now substituting that in, yes, it's a limit problem for h go to 0. Our function this time is changed to a different function, right? So it's the same kind of work, same kind of structure of the problem, but we just apply that to different function. So here I'm looking at 1 plus h to the 4th power minus 4 times 1 plus h, right? Cube, right? And then I'm subtracting 1 to the 4th minus 4 times 1 cubed all over h. Yeah. So this time the 1 plus h to the fourth power is the same as 1 plus h times 1 plus h. That's just a reminder, times 1 plus h, another 1 plus h, right? And times another 1 plus h. 4 identical factor of 1 plus h multiplied together. So, I'm not going to be that insane to make you guys do the foiling work right here in class, right? Verify me. I'm just going to tell you the FOIL work, and then you guys are going to verify that at home. The idea is you got to get your algebra back on the horse, right? So that 1 plus h all to the fourth power, after foiling, it's going to become, so we got 1 plus 4h plus 6h squared plus 4h cubed plus h to the fourth again. Okay. That's how I foiled it. And then the cubic right here, once again, we have done it in the earlier problem. 1 plus h all cubed equals to 1 plus h times 1 plus h times another 1 plus h. Okay. So foiling that, minus, but don't forget there's a minus 4 again. So the 1 plus h all cubed is foiled into 1 plus 3h plus 3h squared plus h cubed, right? Like someone already worked on that earlier for me before. All of that there I'm going to subtract. See? 1 to the fourth power is a 1 minus another 4 here, that's making it negative 3, so it's plus 3 altogether. And we put that over h. So it's some crazy foiling work there. And then some algebra is going to help us to distribute that minus 4 for each term here. So, in my next step, yes, it's a little bit problem. H go to 0, and here I'm looking at 1 plus 4h plus 6h squared plus 4h cubed plus h to the fourth, right? Minus 4 minus 12h minus 12h squared minus 4h cubed, and plus 3 all over h. But when it comes to the step right here, then we're going to have a lot of nice cancellations that will happen, and including the combining like terms. So there are, see, there's 1 plus 3 with the minus 4, right? Those will cancel out nicely. 1 plus 3 minus 4. Right? The 4h cubed is opposite term with minus 4h cubed. Those two are gone as well. Well, doing that. And then there's a 4h, right? So now that's combine like terms and all that. So now looking at h to the fourth is a lone term standing by itself. And then the h cubed that's canceled away. So minus 12h squared with plus 6 gives me minus 6h squared combined, right? And then the minus 12h plus 4h right here combined together gives me a minus 8h. And all of a sudden we realize that that's pretty much everything for after cancellation and combining like terms. So now we can factor out the h. So h cubed minus 6h minus 8. Yeah. We go finding that by h. We're getting h from 0. So that is, we cancel the h. Those are limits, right, of h cubed minus 6h minus 8. Yeah. H comes to 0. So that means those limits turn into a minus 8. But minus 8 means the slope of our tangent line equals negative 8. All right, so we got the slope of tangent line down. So the next step here, we're going to just look for the tangent point, right? So the tangent point here, when x equals 1 as given, we need to substitute this same x value into our beginning function right here, f(1). So y is f of 1, right? But f of 1 in our case here means what? 1 to the fourth power minus 4 times 1 cubed. That makes it what? That's going to make it, so that's a 1 minus an altogether, minus a 4, so minus 3 altogether. So your tangent point here is 1 comma negative 3. Now, after getting the tangent point here, our tangent line currently at this point, after finding slope, right, we're looking at y equals minus 8x plus b, right? That's our current tangent point after we found the slope. And then so now I'm going to substitute in this tangent point into the equation x squared x, y for y. So I'm looking at minus 3 equals negative 8 times 1, right, plus b. Okay. So solving for b, I'm looking at b equals adding 8 over, right? That's going to make it positive 5. Yeah. Okay, so the complete equation now is going to be y equals minus 8x plus 5. That's our equation for the tangent line. This line, if you want to put it on the graph, it's going to be tangent to the function x to the fourth minus 4x cubed, but only at x equals 1. Right?